November 15, 1916, Massillon, Ohio. The engineering assessment from visiting European steel consultants would never fully capture what they witnessed in that American steel mill. German wire drawing specialists, examining production methods that contradicted everything European metallurgy said was necessary for creating bridge cables capable of supporting massive loads. Through the heat and grinding of tungsten carbide dies, Central steelworkers were drawing high-carbon steel wire using techniques that seemed impossible to European observers. Not 6 drawing passes like German tradition demanded, 12 passes, not conventional cooling methods, controlled annealing between each stage, not the established 120,000 pounds per square inch tensile strength European wire achieved, something approaching 210,000. In European facilities, master wire drawers followed centuries-old methods passed down through guild apprenticeships. Each batch required weeks of careful hand drawing through crude dies. Most carried limitations that made long-span bridges structurally impossible. The Americans were operating with metallurgical philosophy the Europeans had declared fundamentally unsound. Multi-stage drawing, precision temperature control, stress-relieving processes between each pass. 4,000 miles from European workshops, the most decisive bridge-building revolution in engineering history was taking shape. Not through superior tradition, not through established methods, but through systematic innovation that would create cables lasting over a century, while modern shortcuts fail in 20 years. The telegram arrived at Central Steel Corporation's headquarters on a gray November morning in 1916, bearing the Pennsylvania and Ohio Railroad's official specifications for what would become the most ambitious bridge project in the American Midwest. William Hayes read the requirements twice before summoning his chief metallurgist to his office on the 3rd floor of the red brick building that overlooked Massillon's industrial district. The railroad demanded a suspension bridge spanning 1,200 feet across the Ohio River Valley, longer than any single span ever attempted west of the Atlantic seaboard. Frank Morrison studied the engineering drawings spread across Hayes's mahogany desk, his trained eye immediately recognizing the challenge that had prompted European consultants to declare the project impossible with American steel methods. The bridge would carry 40-ton freight locomotives hauling coal and steel from Ohio's industrial heartland to eastern markets, requiring wire cables capable of supporting dynamic loads that exceeded anything previously engineered in American manufacturing. Morrison traced his finger along the specification calling for wire with 200,000 pounds per square inch tensile strength, nearly double what conventional American wire drawing could achieve. "The Europeans are right about one thing," Morrison said, rolling up the blueprints with deliberate precision. "Traditional single-pass drawing won't produce wire strong enough for this span, but they're wrong about American capabilities." Hayes leaned back in his leather chair, recognizing the quiet intensity that always preceded Morrison's most ambitious proposals. The metallurgist had spent 3 years working in the Krupp steelworks in Germany, absorbing European techniques while developing his own theories about grain structure optimization. Unlike the bombastic engineers who dominated industry conferences, Morrison spoke in measured tones backed by meticulous research and mathematical calculations that consistently proved correct under testing conditions. The economic stakes extended far beyond Central Steel's balance sheet. 26 steel mills throughout the Ohio River Valley depended on efficient transportation to eastern markets, employing over 40,000 workers whose livelihoods hung on maintaining competitive shipping costs. Without the bridge, freight would continue traveling circuitous routes through Pittsburgh, adding 3 days and substantial expense to every shipment. Morrison understood that failure would reinforce European perceptions of American steel as suitable only for basic construction rather than precision engineering applications. Morrison had been developing multi-stage wire drawing techniques since his return from Germany in 1911, conducting experiments in Central Steel's research facility during off hours while fulfilling his regular metallurgical duties. His process required drawing high-carbon steel containing 0.85% carbon through 12 progressively smaller tungsten carbide dies with controlled annealing at 1400 degrees Fahrenheit between specific passes to optimize pearlite grain structure. European methods typically use 6 drawing passes. Morrison's technique doubled that number while maintaining uniform internal stress distribution throughout the wire's cross-section. The technical challenge went beyond mere tensile strength. Dynamic loading from locomotive traffic created fatigue stresses that could cause microscopic crack propagation over time, eventually leading to catastrophic failure. Morrison's preliminary tests suggested that his multi-stage process with intermediate stress relief could produce wire resistant to fatigue cycles, a property that conventional single-pass drawing could never achieve regardless of raw material quality. Hayes understood the financial implications better than most steel executives. The experimental wire mill would cost approximately $200,000 to construct and equip, requiring specialized tungsten carbide dies imported from Sweden and precision temperature control equipment unavailable from American suppliers. Central Steel's board had approved the expenditure based on Morrison's test, results showing prototype wire achieving 190,000 pounds per square inch tensile strength. But the Pennsylvania and Ohio Railroad contract contained a clause that threatened to derail the entire project. They're requiring wire from established European suppliers, Hayes said, tapping the contract with his fountain pen. The insurance underwriters won't approve American cable manufacturers for a span this long. They consider our industry unproven for critical structural applications. Morrison had anticipated this obstacle. American bridge wire had gained an unfortunate reputation for inconsistent quality due to manufacturers cutting costs through inferior raw materials and simplified processing. Most American wire producers used low-carbon steel with simplified drawing techniques that prioritized production speed over structural performance. The resulting wire met basic construction requirements, but lacked the fatigue resistance necessary for long-term structural reliability under heavy loading conditions. We'll have to prove superiority through testing that European suppliers cannot match, Morrison replied. If our wire exceeds their specifications by a significant margin, the railroad will have grounds to modify their supplier requirements based on performance rather than reputation. The conversation was interrupted by Eric Lindqvist, the Swedish master wire drawer who had been working with Morrison to refine the multi-stage process. Lindqvist knocked once before entering Hayes's office, his work clothes still bearing traces of steel dust from the experimental production line. His weathered hands held a sample of wire drawn through Morrison's 12-stage process, twisted into a tight coil that gleamed under the office's electric lighting. The latest batch tested at 210,000 pounds per square inch, Lindqvist reported in his careful English. Grain structure shows optimal perlite formation throughout the cross-section. No internal stress concentrations detected during microscopic examination. Hayes examined the wire sample, noting its consistent diameter and smooth surface finish. European wire typically showed slight variations in thickness and occasional surface irregularities that indicated inconsistent drawing pressure. Morrison's process produced wire with precision that matched German manufacturing standards while exceeding their strength specifications. The three men understood they were challenging not merely technical limitations, but deeply entrenched perceptions about American manufacturing capabilities. European steel had dominated global markets for decades, supported by centuries-old traditions and university research that American industry supposedly lacked. Proving American superiority would require more than laboratory tests. It would demand flawless performance under the most demanding structural conditions ever imposed on bridge wire. Construction of Morrison's experimental wire mill began in December 1916, transforming a vacant section of Central Steel's facility into the most sophisticated wire drawing operation in America. The project required precision beyond anything previously attempted in American manufacturing, beginning with the installation of 12 tungsten carbide dies imported from Swedish toolmakers who had supplied European steel mills for over a century. Each die measured exactly 1 inch in diameter with drawing holes machined to tolerances of plus or minus 0.002 of an inch, precision that demanded specialized measuring equipment unavailable from American instrument makers. Morrison supervised every aspect of the installation, working 16-hour days to ensure that each piece of equipment met his exacting specifications. The drawing machines themselves represented a hybrid of German engineering principles and American mechanical innovation, with electric motors providing consistent pulling force while steam-powered systems maintained precise tension control throughout the 12-stage process. Unlike conventional wire mills that operated at maximum speed to increase production volume, Morrison's facility prioritized controlled drawing rates that allowed optimal grain structure formation during each pass. The annealing furnaces posed the greatest technical challenge, requiring temperature control accurate to within 10 degrees Fahrenheit during the stress-relieving process between drawing stages 4, 8, and 12. Morrison designed custom furnace chambers with multiple heating zones and thermocouple monitoring systems that provided real-time temperature feedback to furnace operators. The controlled cooling rates proved critical for creating the pearlite grain structure that would give the finished wire its exceptional fatigue resistance. Eric Lindqvist led the recruitment effort to find skilled workers capable of operating Morrison's complex production system. The multi-stage process required 47 operators per shift, working in perfect synchronization, with each worker responsible for specific aspects of the drawing, annealing, and quality control procedures. Lindqvist traveled to immigrant communities throughout Ohio and Pennsylvania, seeking German and Swedish craftsmen familiar with precision wire drawing techniques developed in European mills. The recruitment process revealed the significant wage premium necessary to attract workers with appropriate skills. Morrison convinced Hayes to authorize $4.50 per day for experienced operators, nearly double the $2.25 standard wage in American steel mills. The higher compensation reflected not only the specialized knowledge required, but also the precision and consistency demanded by Morrison's process, where operator error could ruin entire batches of expensive high-carbon steel. Maria Kowalski emerged as the facility's most effective quality inspector, applying mathematical precision learned from her surveyor father to detect microscopic variations in wire diameter and surface finish that indicated internal stress problems. Her visual acuity for identifying color variations during annealing proved invaluable for preventing defective batches from progressing through expensive subsequent processing stages. Kowalski developed inspection protocols that caught material flaws before they reached the drawing dies, preventing equipment damage that could shut down production for days. The raw material requirements pushed Central Steel's procurement capabilities to their limits. Morrison's process demanded high-carbon steel containing exactly 0.85% carbon, significantly higher than the 0.60% typically used in American wire production. The elevated carbon content provided the strength characteristics necessary for achieving 200,000 pounds per square inch tensile strength, but required careful handling during melting and casting to prevent segregation that would create weak spots in the finished wire. James Murphy, known throughout the facility as Hammer for his ability to diagnose furnace problems through sound and vibration, became Morrison's most trusted annealing operator. Murphy's intuitive understanding of high-temperature steel processing allowed him to maintain the precise heating and cooling cycles essential for optimal grain structure formation. His experience with furnace operations dating back 15 years provided the practical knowledge necessary to translate Morrison's theoretical specifications into consistent production results. By spring 1917, the facility achieved stable production of wire meeting Morrison's target specifications. Quality testing revealed properties that exceeded even Morrison's optimistic projections. Tensile strength consistently measured between 205 and 215,000 pounds per square inch, with uniform characteristics throughout each production batch. More significantly, fatigue testing demonstrated extraordinary resistance to repeated stress cycles, with samples withstanding over 50,000 loading cycles without developing measurable crack propagation. The breakthrough came during dynamic loading tests designed to simulate actual bridge service conditions. While conventional American wire typically failed after 2,000 stress cycles under heavy loading, Morrison's wire showed no signs of fatigue damage after 25,000 cycles, more than 10 times the durability of standard wire used in existing bridge construction. The superior performance resulted from the controlled pearlite grain structure created by Morrison's multi-stage process, which distributed stress more evenly throughout the wire's cross-section and prevented the crack initiation that led to catastrophic failure in conventional wire. Word of Morrison's achievements began spreading through engineering circles despite Central Steel's attempts to maintain secrecy during the development phase. Railroad engineers conducting preliminary surveys for the Pennsylvania and Ohio Bridge project heard reports of American wire with strength characteristics approaching European standards. Bridge contractors from across the Midwest began contacting Central Steel, inquiring about availability and pricing for specialty wire applications that previously required European suppliers. Morrison expanded production capacity to 500 tons monthly by late 1917, making Central Steel the largest specialty wire producer in America. The increased output required additional skilled workers and expanded annealing capacity, but Hayes authorized the investment based on growing order backlogs from customers who had tested Morrison's wire and found performance superior to European alternatives. The success validated Morrison's conviction that American manufacturing could surpass established European methods through systematic innovation and precision execution. The Pennsylvania and Ohio Railroad quietly amended their supplier requirements in August 1917, adding provisions for American manufacturers meeting specified performance standards alongside the original language requiring established European suppliers. Morrison's wire had demonstrated capabilities that exceeded the railroad's minimum requirements by substantial margins, providing engineering margins of safety that European suppliers could not match, while offering cost advantages that made the project financially attractive. The validation tests conducted by Pennsylvania and Ohio Railroad engineers in September 1917 would later be remembered as the moment American steel manufacturing proved its superiority over European methods. Chief Engineer Robert Caldwell arrived at Central Steel's facility with a team of structural analysts and testing equipment designed to subject Morrison's wire to loading conditions that exceeded anything previously attempted in American bridge engineering. The railroad's reputation depended on absolute confidence in cable performance, particularly given the 1,200-foot span that would carry the heaviest freight loads in Midwest railroad history. Morrison watched from the observation platform as Caldwell's team installed their hydraulic testing apparatus, a massive steel frame capable of applying up to 300,000 pounds of tension, while simultaneously subjecting wire samples to dynamic loading cycles that simulated locomotive traffic patterns. The test protocol called for sustained loading at 150% of design capacity, followed by 50,000 fatigue cycles at varying load amplitudes, conditions that typically destroyed conventional wire within the first few thousand cycles. The initial static load test produced results that surprised even Morrison. Central Steel wire supported loads of 325,000 pounds per square inch before showing any signs of plastic deformation, significantly exceeding the 200,000 pounds per square inch minimum requirement. More importantly, the wire maintained its original diameter and surface characteristics under maximum loading, indicating that the internal stress distribution remained uniform throughout the cross-section despite extreme tension forces. Caldwell's engineers then subjected the wire to dynamic loading cycles designed to replicate 20 years of heavy freight traffic crossing the proposed bridge. The testing apparatus applied alternating loads between 50,000 and 200,000 pounds at frequencies matching typical locomotive crossing patterns, while monitoring equipment detected any microscopic changes in wire structure that might indicate fatigue damage initiation. Conventional American wire typically showed measurable crack propagation after fewer than 5,000 cycles under these conditions. Morrison's wire withstood the complete 50,000 cycle test protocol without developing detectable fatigue damage. Microscopic examination revealed that the controlled perlite grain structure created by his multi-stage drawing process distributed stress more effectively than the random grain orientation found in conventional wire. The result challenged fundamental assumptions about steel fatigue that had dominated bridge engineering for decades, suggesting that properly processed American wire could outlast European alternatives by substantial margins. The comparative testing against German wire samples provided the most compelling evidence of American superiority. Caldwell had obtained specimens from 3 leading European manufacturers, including wire from the same Krupp facilities where Morrison had learned German steelmaking techniques. Under identical loading conditions, the German wire achieved impressive static strength approaching 200,000 pounds per square inch, but failed after fewer than 30,000 fatigue cycles, substantially less than Morrison's wire, which showed no degradation after 50,000 cycles. Eric Lindqvist observed the testing with particular satisfaction, having spent 3 decades watching European wire drawing techniques reach their theoretical limits. His expertise in traditional methods allowed him to recognize that Morrison's innovations represented genuine advancement rather than mere variation in established processes. The superior fatigue resistance resulted from fundamental improvements in grain structure control that European manufacturers had not achieved despite their longer manufacturing traditions. Maria Kowalski documented every aspect of the testing process, creating detailed records that would later serve as the foundation for American wire manufacturing standards. Her mathematical background enabled her to recognize the statistical significance of Morrison's results, calculating that the probability of achieving such consistent performance through random variation was essentially zero. The wire's properties represented systematic advancement in metallurgical science rather than fortunate accident. News of the test results spread rapidly through the steel industry, despite Central Steel's efforts to maintain confidentiality during the evaluation period. Railroad engineers from across America began requesting specifications for Morrison's wire, recognizing that superior fatigue resistance could extend bridge service life far beyond anything previously considered possible. Bridge contractors calculated that wire lasting 50 years instead of 20 could justify premium pricing while still providing substantial cost savings to railroad operators. Orders began arriving at Central Steel before Caldwell completed his final engineering report. The Missouri Pacific Railroad requested wire for a 900-foot span across the Arkansas River. Pennsylvania Railroad engineers inquired about availability for replacing aging cables on their Ohio River crossing. The Santa Fe Railway commissioned preliminary studies for a proposed bridge in Arizona that would require wire performance approaching the theoretical limits of steel construction. Morrison expanded production planning to accommodate the growing demand, but recognized that scaling his process required additional skilled workers and specialized equipment that remained in short supply throughout American industry. The 12-stage drawing process demanded precision that few American workers possessed, while the tungsten carbide dies necessary for consistent results required months of advance ordering from Swedish suppliers who served European steel mills as their primary customers. Hayes authorized construction of a second production line in October 1917, doubling Central Steel's specialty wire capacity while maintaining the quality standards that distinguished Morrison's product from conventional American wire. The expansion required recruiting additional Swedish and German craftsmen while developing training programs to teach American workers the precision techniques necessary for consistent results. The Pennsylvania and Ohio Railroad's final approval came in November 1917, with Caldwell's engineering report concluding that Central Steel wire exceeded all performance requirements by margins that provided exceptional safety factors for the proposed bridge design. The railroad's board voted unanimously to proceed with American suppliers, marking the first time a major infrastructure project had chosen domestic wire over European alternatives based purely on superior technical performance. Morrison's achievement resonated throughout American industry as proof that systematic innovation could overcome centuries of European manufacturing advantage. Steel executives who had previously dismissed American capabilities as suitable only for basic construction applications began investigating opportunities to challenge European suppliers in precision manufacturing markets that had seemed permanently beyond American reach. The explosion occurred at 11:47 on the morning of December 14, 1917, when James Murphy was conducting routine temperature monitoring of the No. 3 annealing furnace during the critical stress-relieving phase for a batch of high-carbon steel destined for the Pennsylvania and Ohio Railroad project. The blast shattered windows throughout Central Steel's facility and sent a column of black smoke rising above Massillon's industrial district, visible from 10 miles away as emergency crews rushed toward the plant. Murphy survived the initial explosion, but suffered severe burns across 40% of his body while attempting to shut down the gas lines that fed the compromised furnace system. 3 other workers, Swedish immigrants Lars Andersson and Niels Bergman, along with Polish-American quality inspector Stefan Kowalski, Maria's younger brother, died instantly when the furnace chamber ruptured, sending molten steel and superheated gas throughout the annealing facility. The force of the blast destroyed 60% of Morrison's carefully calibrated production equipment, including 8 of the 12 precision tungsten carbide dies that had taken months to obtain from Swedish suppliers. Morrison arrived at the facility within minutes of the explosion, finding Eric Lindqvist directing evacuation efforts, while Maria Kowalski searched desperately through the wreckage for her brother. The annealing building had collapsed on the eastern side where the number 3 furnace had been located, leaving twisted steel beams and scattered equipment where Morrison's revolutionary wire drawing process had operated with mathematical precision just hours earlier. The acrid smell of burned steel and gas hung over the facility as firefighters worked to prevent the blaze from spreading to Central Steel's main production areas. The preliminary investigation revealed that the batch of high-carbon steel processed immediately before the explosion contained excessive sulfur impurities that had created gas pockets during the heating process. When Murphy raised the furnace temperature to the standard 1400 degrees Fahrenheit required for proper annealing, the trapped gases expanded explosively, rupturing the furnace chamber with force equivalent to several pounds of dynamite. The defective steel had come from a new supplier in Pennsylvania who had guaranteed chemistry matching Morrison's specifications, but had apparently failed to control sulfur content during the smelting process. Federal safety inspectors arrived from Washington within 48 hours of the explosion, shutting down Central Steel's entire wire drawing operation pending a comprehensive investigation into Morrison's manufacturing processes. The timing proved catastrophic for American Steel's reputation, as the accident occurred just 3 months after the United States entered World War I, when government officials were particularly sensitive to industrial safety issues that might disrupt military production. Steel allocations previously destined for bridge construction were immediately redirected toward munitions manufacturing, leaving civilian infrastructure projects without reliable material sources. Morrison's carefully assembled workforce began dispersing to other employment within days of the shutdown, as skilled craftsmen could not afford to wait indefinitely for production to resume while supporting their families on uncertain prospects. Eric Lindqvist received offers from 3 different steel companies, seeking his expertise in conventional wire drawing, while Maria Kowalski was recruited by Republic Steel Corporation in Cleveland for their quality control department. The loss of trained personnel threatened to eliminate years of accumulated knowledge about Morrison's specialized processes, even if government inspectors eventually approved resuming operations. European competitors moved quickly to exploit Central Steel's misfortune, circulating technical analyses suggesting that Morrison's multi-stage drawing process was inherently dangerous due to the high temperatures and pressures required for optimal grain structure formation. German steel consultants published papers in engineering journals arguing that American manufacturing lacked the centuries-old safety traditions necessary for high-temperature metallurgical processes, while offering immediate delivery of proven safe conventional wire at premium prices to customers concerned about production delays. The Pennsylvania and Ohio Railroad faced intense pressure from insurance underwriters and financial backers to cancel the bridge project entirely rather than risk association with manufacturing methods that had resulted in fatal accidents. Railroad executives who had enthusiastically endorsed Morrison's wire after witnessing its superior test performance now worried that public perception of American steel safety might create liability issues that could affect the company's broader operations. European suppliers who had been displaced by Morrison's innovations began submitting revised proposals offering conventional wire that met minimum engineering requirements without the perceived risks of advanced American processes. Hayes confronted the possibility that Central Steel might face bankruptcy if the government investigation concluded that Morrison's processes violated federal safety standards for industrial operations. The company had invested nearly $400,000 in specialized equipment and facility modifications, money that would be completely lost if regulators prohibited high-temperature annealing operations. Insurance claims for the destroyed equipment and worker compensation would consume most of Central Steel's remaining capital reserves, leaving little funding available for rebuilding even if government approval was eventually obtained. Morrison spent sleepless nights reviewing every aspect of his manufacturing process, searching for design flaws that might have contributed to the explosion while wrestling with guilt over the deaths of 3 skilled workers who had trusted his innovations. His detailed production logs revealed no previous incidents involving sulfur-contaminated steel, suggesting that improved quality control procedures for raw materials might prevent future accidents without abandoning the multi-stage drawing process that had proven capable of producing superior wire. The investigation dragged through the winter months of 1917 and early 1918 as federal inspectors struggled to evaluate manufacturing processes that exceeded the technical knowledge of most government engineers. Morrison provided exhaustive documentation of his methods while working with safety specialists to develop enhanced protocols for detecting defective raw materials before they entered the production system. The delay allowed rumors and speculation to circulate throughout the steel industry, further damaging American wire manufacturing's reputation, just as European suppliers were regaining market confidence. By February 1918, orders that had been placed with Central Steel were being canceled as customers switched to European suppliers who could guarantee immediate delivery. The momentum that Morrison had built through superior technical performance evaporated as practical concerns about production reliability outweighed engineering advantages that customers could no longer access. American steel manufacturing's brief challenge to European dominance appeared to have ended in the rubble of Central Steel's destroyed annealing facility. Morrison emerged from the wreckage of December's explosion with insights that would transform American steel manufacturing beyond his original innovations. The investigation had revealed that sulfur impurities in raw steel created the gas pockets responsible for the catastrophic furnace failure, leading Morrison to develop partnership agreements with iron ore suppliers in Minnesota's Mesabi Range who could guarantee ultra-low sulfur content through careful mining and processing techniques. The new sourcing arrangements required premium pricing for specialty ore, but provided the material purity essential for safe high-temperature processing. The rebuilt facility that took shape during the spring of 1918 incorporated safety improvements that exceeded government requirements while maintaining the precision necessary for Morrison's multi-stage drawing process. Enhanced furnace design provided more accurate temperature control through multiple heating zones with independent monitoring systems, while spectrographic analysis equipment examined every batch of raw steel before processing began. The new quality control procedures could detect sulfur content variations as small as 0.005%, preventing contaminated material from entering the production system. Eric Lindqvist returned to Central Steel in March 1918, bringing with him 2 additional Swedish craftsmen who had worked in Stockholm's precision wire mills and understood the exacting standards necessary for consistent results. The expanded workforce allowed Morrison to implement enhanced training protocols that documented every aspect of the drawing process, creating written procedures that reduced dependence on individual worker knowledge while maintaining the craftsmanship traditions that distinguish superior wire from mass-produced alternatives. Maria Kowalski's decision to remain with Central Steel despite attractive offers from competitors proved crucial for re-establishing production quality after the lengthy shutdown. Her mathematical approach to quality control had evolved during the rebuilding process, incorporating statistical analysis techniques that could predict material behavior based on microscopic examination of grain structure patterns. The enhanced inspection methods caught potential defects during early processing stages, preventing expensive equipment damage and ensuring consistent wire properties throughout each production batch. Government approval for resumed operations came in April 1918, following exhaustive safety inspections that validated Morrison's enhanced procedures while establishing new industry standards for high-temperature metallurgical processes. Federal inspectors acknowledged that Central Steel's rebuilt facility represented the safest steel processing operation in America, with redundant safety systems and quality controls that other manufacturers would be required to adopt for similar high-risk applications. Production resumed with 0 safety incidents, while achieving wire quality that exceeded pre-disaster standards. The enhanced furnace control systems provided more precise temperature regulation during annealing cycles, resulting in optimal perlite grain structure formation throughout the wire's cross-section. Testing revealed tensile strength consistently above 210,000 pounds per square inch, with fatigue resistance approaching theoretical limits for carbon steel construction applications. The Pennsylvania and Ohio Railroad had maintained their commitment to American suppliers throughout Central Steel's rebuilding process, recognizing that Morrison's technical innovations offered long-term advantages that outweighed temporary production delays. Construction of the 1,200-foot suspension bridge began in June 1918, with Central Steel providing wire cables that would be subjected to the most demanding service conditions ever imposed on American-manufactured steel products. Hayes expanded production capacity beyond pre-explosion levels as orders resumed from customers who had witnessed Morrison's determination to overcome the manufacturing setbacks while improving safety and quality standards. Bridge contractors throughout America had observed that European suppliers could not match the fatigue resistance demonstrated by Central Steel wire, leading to specifications that increasingly favored American manufacturers who could meet enhanced performance requirements. Morrison's process became the foundation for American wire manufacturing standards as competing companies attempted to replicate his results through reverse engineering and industrial espionage. The multi-stage drawing technique with controlled annealing spread throughout the domestic steel industry, though few manufacturers achieved consistent results without the precision equipment and skilled workforce that Morrison had assembled over years of systematic development. The bridge opened to traffic in November 1918, coinciding with the armistice that ended World War I and marked America's emergence as a global industrial power. Morrison's cables performed flawlessly under the heaviest freight loads in American railroad history, carrying 40-ton locomotives across the Ohio River Valley without measurable deflection or stress-related deterioration. Dynamic testing conducted during the first months of operation revealed no fatigue damage after 50,000 locomotive crossings, validating Morrison's predictions about superior durability. By 1920, Central Steel supplied wire cables for over 200 bridges across America, establishing domestic manufacturing as the preferred source for critical infrastructure applications that required exceptional reliability and longevity. Morrison's techniques had evolved beyond their original German influences to create uniquely American methods that surpassed European performance standards while incorporating safety innovations developed through hard-won experience with high-temperature metallurgical processes. The merger with Republic Steel Corporation in 1930 preserved Morrison's manufacturing methods as the foundation for American specialty wire production throughout the 20th century. His processes remained the industry standard for high-performance bridge cables, producing steel that continued supporting traffic loads decades after installation, while bridges built with conventional wire required expensive cable replacement every 20 to 25 years. The lasting vindication of Morrison's innovations appeared most dramatically in longevity comparisons conducted during the 1990s, when bridges constructed with his 1916 process still carried traffic after 75 years of service without cable replacement. Meanwhile, highway bridges built during the 1970s and 80s using cost-optimized single-pass drawing techniques required $12 million cable replacement projects after stress corrosion failures developed within 20 years of installation. Morrison's achievement demonstrated that superior materials demanded superior processes, establishing principles that guided American manufacturing excellence throughout the industrial age. His systematic approach to metallurgical innovation proved that American engineering could surpass established European methods through persistent experimentation, precision execution, and unwavering commitment to technical excellence over production shortcuts that compromised long-term performance for immediate cost savings.